Welcome to Let's Code. I'm here with my usual hand-picked crew of students, faculty and special guests at the Bitfield Institute of Technology. I'm here with Adebayo. Hello.
Hello, John.
Bukola joins us. Hi there.
Hello.
And Umang is with us. How are you doing?
I'm doing good. Hello, everybody.
So this week I thought we'd do something a little bit different. We talked a lot about randomness last week, and we asked some questions like, what does it mean for things to be random? And how does math round work in Go? And how does crypto round work in Go? And we thought, if you're in the business of generating passwords, you know, how random do you need passwords to be? And is it possible to generate a password so random that even God can't guess it? And we decided it was, if you use quantum randomness. Of course, God doesn't need to guess your password. So the question is moot, but it's worth knowing, isn't it? So this week I thought we might continue that line of thought and think about passwords. So we are looking at a library in Go for measuring the strength of passwords, which is an interesting idea, isn't it?
Yes.
What does it mean for passwords to be strong? And we can think about that and we can try and work out how to do it. And if you're wondering why you're not seeing any code, it's because we haven't written it yet. There are libraries for validating passwords and checking the strength and so forth, but we don't need those. We're coders. We can write stuff. Should we have a go by ourselves?
Sure.
Let's do it.
It's like telling a songwriter there's already a song about love, isn't it? We just feel like, let's have a go and see what we can do. So I've got a great crew on hand today, so I think we can do something. Let's think about the problem for a minute and just get our brains all sort of lined up and running. So if we think about passwords, I mean, you can generalize the idea of passwords to some sort of key, can't you?
Yes.
Maybe I want to send a secret message to somebody, or maybe I just want to protect my login, or maybe I want to use some key to encrypt conversations or to do anything. But we have some sort of sense intuitively of what the strength of a key means, don't we? Can we sort of tease that out a little bit? Anybody like to try and say what they think contributes to password strength, let's say?
A couple of things, I guess. John, I can go. Length of the password.
Yep. That's an important one, isn't it?
Yes.
We feel intuitively that short passwords are not as good as strong passwords, although maybe we haven't exactly quantified why. Anything else you can think of?
What is the password made of? Letters, numbers, characters, sort of things, wildcards kind of stuff.
Yeah, and why is that? I mean, maybe I'm asking super obvious and dumb questions, but those are the kind of questions I like to ask because the answers are often interesting and surprising. Why is a long password better? And why is a password that contains more different kinds of things better than one that doesn't?
Yes, to
No?
Well,
randomize.
Can you say a little bit more?
It's easier to randomize if it's longer, I think.
Yeah. When you say randomize, what exactly are you saying? Just to be super clear.
To generate or create unique passwords. That's what I mean. Because if they're shorter, then I mean you can only have so many permutations of the same length. I think.
Yeah, that's right. It's like we talked about the combination locks last week, isn't it? If you have a suitcase with just one digit combination lock, that's rubbish. It's not much better than not having a lock at all, is it? Because you could easily try all 10 possible combinations. Adding another wheel multiplies the number of possibilities by 10, so it just takes 10 times longer to guess them all, doesn't it?
too much.
So maybe we can think about this in terms of, let's look at it from the point of view of someone who's trying to crack a password. What do we mean by cracking? Probably just guessing the right key, isn't it?
Correct.
So what would we do then? If we put our evil hats on for a moment, let's say we're black hat password crackers, we could write that in Go, but what would we do? Let's make it concrete. Let's say there's there's a Bitcoin wallet with $1 million in Bitcoin inside, and it's in an encrypted zip file, and if we only knew the password, we'd be richer by $1 million. How would we go about guessing that password?
You just go guessing each key combination, as you said. So we might have.
Yeah, I think it really is as simple as that, isn't it? We would just simply try every possibility. Now, obviously we could be smarter than that. I mean, if we know, we might start by guessing the person's name, the top 10 most popular passwords like password, secret, Fred, all of these things. But that's just another order of enumerating all the possible passwords, isn't it? We're just saying we're going to try them all, but we'll try the obvious ones first.
Yes.
Suppose we generalize it completely and just say, let's just think about it in terms of a number. When we think about passwords, we're usually saying numbers, letters, maybe some special characters. But fundamentally, you can boil it down to a number, can't you? And in things like TLS and crypto keys, it really is just a long string of bits. So let's get some helpful concepts for thinking about password strength in terms of, shall we say, the size of the key space. Is it clear what that means?
Is that the number of characters involved?
Yeah, that's part of it, isn't it? When we say key space, it's just a technical way of saying the number of possible passwords, isn't it? So what contributes to the key space? How could we work out what the key space is for a given password? Anyone like to try?
When we're talking about the numeric aspect, you're saying like 8 byte 16, that's something of that sort. Are we looking at?
Yeah, but how would we do it in principle? So suppose I told you I'm thinking of a number from 1 to 10. What's my key space?
Integer key space, that whatever the int might be.
Yeah, it's 10, isn't it?
It's 10. Basically, it's 10. Yes, correct. Yes.
And if I said I'm thinking of a number from 1 to 100, the key space is 100. And how many tries do you think it would take you to guess the number on average?
On average, maybe average, the worst case would be like 10. If you go to out of 10, if you go 100 would be 100, but average maybe 55, half of it.
Yeah, we can put an upper bound on it by saying if we have 100 guesses, assuming they're all different, we will have definitely guessed it. If we make no tries at all, we definitely can't guess it. The median number of guesses it's going to take is 50, isn't it?
Yes.
So that's perhaps a useful way of thinking about key strength, is, the time, or the tries needed to exhaust the key space is 100 in our example. But half the time we'll have guessed the password quicker than that, so perhaps, the median number of tries required is maybe a useful way to think about that. So there's also the question about, so we've said the more digits there are in the key, or the more bits, if you like, the better. Also, the number of possibilities per character, that also increases the number of bits, doesn't it? What else could make a password more secure? And what does security actually mean? We're really getting into some basics today, aren't we? But I think this is something most programmers don't spend a whole lot of time thinking about, and maybe they should.
I feel called out.
Yeah, if I tell you I have, tell you my bank password is 4 characters, let's say, is that strong enough?
No.
Why not? I mean, I agree with you. I just wonder if we can elaborate on exactly why.
Because that, I mean, I can try guesses, which will probably give me, I'll probably have less, number of tries to guess what your password will be.
Yeah, if we know it's a number, let's say, then you've got 10,000 possibilities. So it wouldn't take you a super long time to get through all of those, but it would take you some non-zero time to try each one, wouldn't it?
Hmm.
I don't know how long, a few seconds maybe. So let's say, say it takes you 1 second per try, that's 10,000 seconds. So we're saying 5,000 tries on average you'd need to guess it. So 5,000 seconds is about an hour and a half or something like that, isn't it?
Yes.
So what we're saying is if I have a 4-digit PIN, you can crack that in something like on the order of hours, let's say. That doesn't give me a huge amount of confidence in the security of my vast fortune. Because if I had a small fortune, maybe I wouldn't be quite so worried. So that kind of clues us into something else, doesn't it? We actually have to think about the value of what's protected by the password. You need a stronger password for more valuable things than for less valuable things, let's say. And there's one other thing we didn't think about, is the time it takes to try. So if you take off the black hat for a minute and put another one on and say, I am now the system designer who's trying to build a secure system, what could I do to improve the security of my password system? We've said we could make the key longer. We could require the key space to be larger because there's more possibilities for each character. What else could we do?
Are we going into like multi-factor authentication kind of stuff here?
Maybe.
That might be another way to have multiple levels going in.
Yeah, but suppose for any given level of authentication, there's some degree of strength to it, isn't there? How could we beef up the security on the password entry, let's say?
We can find some way to increase the degree of randomness, the entropy.
Yeah, that's a good point. And would expect you to say that because I know that you're building a quantum password generator in your non-existent free time, aren't you? So you're quite interested in randomness, and that's a very good point. Is if the bad person can predict what the password is going to be, obviously it doesn't matter how long it is, If you have a 10,000 character password, but then you write it down and I get a copy, then it doesn't help you at all, does it? So degree of randomness is an important thing. What else could we do? It's difficult for us to ensure that as the bank's software architect, though, isn't it? What could we do as a reasonably simple measure to just make it harder for people to brute force a password?
Maybe a combination of like numbers, vectors, or something with that kind of help.
Yeah, well, one simple thing we could do is just make it take longer to try each password, isn't it?
Mm-hmm.
And you do see this in some systems where if you get it wrong the first time, you have to wait 2 seconds before you can try again. If you get it wrong that time, you have to wait 4 seconds and it keeps doubling. Or maybe after 3 tries, it just erases all the data. That's, wouldn't work with bank accounts, but with some things that is the case, isn't it? I think iPhones do this. You ever get that sense of growing fear? You've entered your PIN wrong 3 times in a row and you think, oh my God, how many more tries do I have? So that's sort of giving us another clue, isn't it? That maybe the length of time it takes to try a password is also a factor. So you could imagine, if you want to make something more secure without increasing the length of the key, you could just increase the time it takes to try it and maybe build in increasing delays. If you have some system with a small key, that's one easy way to get more security. So we started out by saying that length is important, but actually it's, if you can do 1,000,000 tries a second, all of a sudden a 4-digit key doesn't seem quite so good, does it? So are we any closer to answering the question, what does it mean for a password to be strong enough? How could we even phrase that question, do you think? If we were going to write a useful library where you could say, if the user enters a password, is it strong enough? How would you frame that question?
Something that is difficult to guess or crack.
Yeah, can you develop that point a little?
It's kind of random enough that the length might be a couple of points length, kinds of characters, and as you enumerated, the difficulty to break it tries in that sense takes longer to get to it.
Yeah, that's certainly how I think of it. Is as a password user, let's say, I'm primarily concerned about how long is it going to take someone to crack my password. If the answer is an hour and a half, like Bukola cracking my bank password, that's, that wouldn't be strong enough. If it took her 100 years, then I'd be fairly relaxed because maybe she'll break into it, but I'll be long gone, so I won't care. Maybe my descendants and the trustees of my estate will care. But I could easily say, okay, just make it 10,000 then by, perhaps even my legend won't live that long. So really we're saying there's some span of time, isn't there, for a given piece of information with a given value in a given context. There's some length of time if the median cracking time of the password is greater than that, then we're happy, aren't we?
Yes.
And clearly that would be different for different things. But if we said, suppose we said as a sort of default rule of thumb, if it's more than 100 years, then you're all good.
That works.
Yeah. So things like state secrets or, nuclear codes and things, maybe you need longer. But for ordinary folks like you and me, that might work. But there's a factor that we haven't thought about, isn't there, which is who is doing the cracking and how much compute capability are they able to throw at it. If you're one person with a laptop trying to crack my password, you might be able to try X million keys a second or something. If you're a state level actor, or a government or a national security agency or something like that, you presumably have plenty of computers to throw at the problem, billions and billions of dollars worth. So if you need to protect your secret from a government, you might say, so I still want to set a limit on the cracking time, but now they can maybe crack it much more quickly than someone else. So it feels like there's 2 factors in play here, isn't there? It's the number of, let's call it the number of tries per second, the try rate, and the median cracking time. So we've said what would be a reasonable number for the cracking time in a few centuries. What would be a reasonable figure for the try rate? Well, it depends what a try is. Very often it's something like a hash, isn't it?
Yep.
So if we were to do, say, the SHA-256 hash of the password, say, because passwords are often stored as hashes, aren't they? So if we can guess a password, hash our guess, and compare it with the stored hash, as soon as they're equal, then we know we found the password. So we're more or less constrained by how many hashes we can do per second, aren't we? What's a reasonable figure for that? Anyone like to guess? Who's interested in doing a lot of hashes per second? There's a large and well-resourced group of people who are very concerned about this.
Bitcoin, crypto mining guys.
Right, exactly. So almost all cryptocurrencies are based on some kind of hashing. So Bitcoin mining is effectively just doing a ton of hashes per second. And you can buy specialized hardware for this, specialized ASICs. But most GPUs are pretty good at hashing. I think I saw a figure for one GPU of something like 8 billion hashes a second. So let's call it 10 gigahashes. So now we have some useful tools for thinking about this, don't we? Because we can say for any given password we have a way of working out what's the key space. From the key space we know how to work out the crack time, and if we know the try rate or the gigahash rate, let's say, then we know how long it'll take to crack on average. So we might be able to start work, mightn't we? So what should we do? Should we start with it? Should we start with a test?
Yes.
Let's do that.
Yeah.
So let's suppose we start by trying to just gauge the strength of an arbitrary password. So let's say we have something like test strength. What's our want? What would the answer be in the form of? Suppose we had a key.strength function. What would it take and what would it return? Any thoughts?
The key space and return the length of time it would take to guess it, something like that.
Yeah, suppose. Well, let's do that. So let's try and work out the key space for a given password. So let's say, so suppose we call key.space. What do we need to send it?
Password length.
Is that enough though?
Other things you might need, is it in the numeric space, alphanumeric space, something like that?
Yeah, suppose we just send it a password. I mean, if we're thinking about a library for web developers, let's say, they say, please register at Happy Fun Books, let's say. Please enter your password. No, I'm sorry, that password is not strong enough. So we would be taking in a password, which is presumably a string. So let's suppose we said something like hello. So what's key.space going to return? Something, right? It's no good otherwise. Suppose I asked you to work out by hand what's the key space of the string hello. Any ideas?
It's like 26 into 5, 26 alphabets into 5 times.
Yeah, let's make it even easier by just saying it's one character. That's not a mega strong password, but I'm sure that's some people's password. If you're watching at home and this is your password, please change it now. So the thing we need to know is how many possibilities there are, don't we?
Correct.
And let's say if it's only letters, as you said, let's say it's only lowercase letters, that's 26, with 26 possibilities. I feel like the answer should be 26, don't you?
Yes.
Well, that's a useful answer because that helps us work out. Now we know the median number of tries you need. It's half of 26, which is 13. And if you can do 8 billion tries a second, we know that the median crack time of that password is very much less than a second. So far so good. So what do we want? We said we want 26, right?
Yeah.
Okay. And now we know what to write here. This is standard. Okay, are we ready to run this test yet?
Already, yeah.
We can try, can't we? Yeah, cannot find main module. Okay, that's perfectly fine. Let's initialize the module. Let's call it key. Key package is undefined. Okay, let's define it. I just want to take a moment to tell you about a series of ebooks I'm writing for Go beginners called For the Love of Go. In Book 1, Fundamentals, I show you how to write tests in Go and how to build programs test first. In Book 2, Data, I tell you all about variables and values in Go and data types like slices and structs. If you're new to programming or just new to Go, I'll show you everything you need to know to start building fun and useful projects. Go to bitfieldconsulting.com/books and enter Code Club at the checkout to get 25% off now. We're well on top of this, aren't we? I didn't import it. Undefined key.space. Okay, that's perfectly fair, isn't it? Let's define that. We already decided what it takes. Let's call the key K. And let's have it return, say, int. Simplest thing to do is just return 0. So let's do that. Want 26, got 0, so I believe that. So what do we need to do here? You can say return 26. that won't be wrong. But it might take us a while to get to where we need to go. So suppose we already decided that we need to know how many possibilities there are per character out there. So you know, if you dealt, suppose you dealt with arbitrary binary keys, just a slice of byte, let's say. It's pretty easy to find the key space, isn't it? Because we know there's only 2 possibilities for each bit. It can only be a 0 or a 1. So each extra bit doubles the possibilities. So it would be 2 to the power of n for n bits, right?
Yes.
Can we generalize that then? So the number of possibilities per digit to the power of the number of digits. That's a reasonable way to think about it. So how many possibilities are there for, let's say, we're interested in the kind of passwords that you can type into a web form. So you're not going to be pasting, you know, 256 binary digits into a web form. So clearly we're not limited to just lowercase letters, are we? What else could we have?
Uppercase letters, numerics,
Yep.
special characters.
Yep. It's probably, I mean, if we think about Unicode, because Go strings are Unicode, aren't they? There's something like 150,000 Unicode characters, which is a lot, isn't it? So 150,000 to the power of n is going to be a big number. But is it really reasonable to assume that people will use the entire Unicode space? Probably not, right? Even if we assume the person is smart like us and they use a password manager that generates secure passwords, most websites probably won't accept arbitrary Unicode characters because they're not written in Go, so therefore they would probably just crash or reject it or something. So what do we think? What should we limit ourselves to based on the fact that we're dealing with sort of web passwords? Joy, do you have any thoughts about this? Should we limit ourselves to just alphanumeric characters, for example, or should we work with more?
Hello, good day.
Hi, thanks for joining.
Thank you. I think it would be a great idea to put the other characters into consideration. You know, putting that in mind with the password manager if a website is going to be able to get that or something. But I think it's quite a lot.
Yeah.
Having 1,500 of them or something.
Yeah.
Quite a lot.
Now, I know you specialise in bank heists, don't you? So you've probably got a lot of experience in code cracking combination locks.
That's right.
And similar things. So I think that sounds like good advice. So I think we should include the letters and numbers and as many special characters as we can reasonably expect people to type on a keyboard. So I think it's something like about 100 or so characters. So shall we say it's 100 possibilities? Let's make that a constant. We may tweak this, but let's say, so let's call this something like typable characters. 100, okay. So we have a key of a given length. We know how many possibilities we're assuming for each character, so can we work out the key space? Just have a go. There are no wrong answers. Well, actually, there are an infinite number of wrong answers, but you know what I mean.
100 times 100 raised to the length of the string. Which one would be like 100?
Yeah, it's definitely a function of the length of the string and of the possibilities. So we said that it was x to the n, didn't we, for n digits. So we've got typable characters and we've got length of k. How can we raise typable characters to the len of kth power? Is there a standard library for that? That would be great, wouldn't it? I feel like it's going to be in the math library.
Yeah.
That would make sense, wouldn't it? Should we see what we've got? Math dot.
Yeah.
Let's import math. Always a good idea. It was a bad idea to import runtime, and it's always a good idea to import math, whether or not you need it. Right, that isn't helping me. I happen to know MathPow will do what we need. So that will, if we give it typable characters, we'll raise that to len of kth power. So just as a sanity check, suppose we had 2 bits. Each of those bits can be 0 or 1, so that gives us 4 possibilities, doesn't it? Check my math for me.
Correct, yes.
So the key space would be 4 because there's 2 to the 2 possibilities. 3 bits would be 2 to the 3 because twice as big a key space as 2 digits. So that sounds reasonable. So can I just return this?
Yeah.
I've got this wrong, haven't I? It's a good job I've got you all here to help me. There's this saying, can't use MathPower returns a float 64. I can't use that as an int. But we know it must be an integer, mustn't it?
Yes.
The key space only has X number of possibilities, and we can't have a fractional possibility. What can I do here?
Convert?
Yeah? How can I do that? Suppose I have a float 64, which is what I have, and I need an int. How can I turn one into the other? Any suggestions?
Well, I think there's the option of direct casting.
Yep.
And possibly some sort of library for the conversion.
Yeah, we can definitely do a direct type conversion. As you say, we just give the type name that we want and some value that can be implicitly converted, or explicitly in this case. It doesn't like len. Not sure why. Oh, because that needs to be a float 64 as well, so let's do the same thing there, just give the type name and brackets. Okay, how are we looking? Does this look good?
No, wait.
Let's give it a try. Ooh, that's interesting. 126 got 100. What's up with that?
Now we've changed the test definition. We generalize it, right? This is we're looking only the alphabet space. And within our function, we're looking at a lot more.
Yeah, that's a fair point, isn't it? So we said actually we're now dealing with a bigger space
Yes.
than we had. So if we've said there's 100 possibilities for each character, then for a 1-character password, the math is easy, isn't it? It's 100. So should we say want 100?
Mm-hmm.
This should pass. Okay. That seems good to me. Let's do a thought experiment. Suppose we add an extra letter to this. What should the answer be now?
100 times 100.
Yep. Sounds believable. Let's try it. Bingo! Alright. So I believe that our code is doing the same thing we think it's doing, isn't it? So what can we do next? Suppose we said, great to know the key space, but if I don't know how quickly my adversary can enumerate the key space, that doesn't really help me know how strong it is. So, but we might already be taking a leap ahead of most typical password handling code, mightn't we? Because almost all of those just look at the length of it and say, the longer the gooder. You know, but we're thinking a bit more sophisticated than that, aren't we? So we're thinking in terms of given the try rate, we want a certain median crack time. So what can we do to figure that out? Suppose we wanted to ask the question, how many tries would it take? That's a good starting point, isn't it?
Right, yeah. No. So we have a try rate, we said, right? Like,
Yeah.
looking at the bigger stuff.
So yeah, so suppose we had a function like median crack time.
Mm-hmm.
That would be useful, and obviously it would use the space function we already wrote. So let's
Correct.
try that. I say median crack time just to make it super clear, because it's possible to get mixed up between the time to exhaust the key space and the average time, which is half of that, isn't it? So if we say median, that makes it extra clear. So what's our want then? We don't know. So let's work from the inside out. This is a trick I often use. First of all, let's call the function. Median crack time. We'll have to give it a key, won't we?
Mm-hmm.
What else?
We should do a try rate, something.
Yeah, that's the other thing we need, isn't it? So suppose we said the try rate is 1 per second, right? It makes sense for it to be per second, doesn't it? So, okay. So we have our got. So what is that?
So in our example, for example, we want this two string of length 2, that's 10,000. So it's like, in that example, try rate is only like 10,000 seconds, something like that sort. So we want the median of that.
Yeah. So we said for the password, for a 2-character password, the key space is 10,000. We already proved. So halfway through the key space is 5,000.
Correct.
So that's how many tries we need, and at 1 try per second, that's 5,000 seconds, isn't it? So actually we could say maybe this value is a time dot duration, which it is, although I think in practice that's going to be a problem, because a time dot duration is really expressed as a number of nanoseconds, and we're going to be dealing with very large numbers of nanoseconds. Like, it's a billion before you've even got to 1 second, isn't it?
Yes.
We're talking in times of centuries, so that's probably going to be outside the range of, I don't know what the maximum value of a time dot duration is, but I imagine it's not many centuries. So suppose we just say it's a number of seconds. That's reasonable, isn't it?
Yes.
We probably don't have any passwords that, you know, we wouldn't want a password that could be cracked in 1 second, but that seems like a better unit than nanoseconds, certainly, doesn't it? Maybe we should even work in years or something like that, but let's go with seconds. So now we know our want, don't we? What is it?
In this case, for this specific example, it's like 5,000 seconds.
Yeah, that sounds believable. Okay, so now we need to write at least a skeleton function. And we said try rate is, let's suppose that's a uint64, because we can imagine the try rate being quite large, can't we? We already said just a consumer GPU is like 10 to the 9 hashes per second. We can fit that into a uint64. We might even need more, so we might need to go to math.big for arbitrary precision numbers. In fact, Rob Pike made a very interesting proposal to just make int in Go be arbitrary precision, which would be really cool, wouldn't it?
That would be interesting, John. Yeah, arbitrary.
I think in Scheme, for example, numbers are just arbitrary precision by default. You don't need to do anything special. You just find they never overflow, which is great. Because as long as I have free memory on my computer, there's no way the computer should be telling me, sorry, I can't represent that number in the amount of bits I have available. Just throw more bits at the problem. And that's exactly what math.big does. I don't think that proposal is going to be adopted, by the way, which is a shame.
But don't you think there'll be some sort of performance cost?
Oh yeah, absolutely. Yeah, huge performance cost. But I don't care about performance, as you all know. Just if you're worried about that, just buy a faster computer.
Yeah.
So, okay, help me implement median crack time then. Who can start us off?
We will need to find the space for this, right?
Yes, that's true, isn't it? We know it's going to be. We need to say first of all, how many things do we need to try on average, and then we know how fast we're trying, so we can return the time it'll take us. So how many things do we need to try? That's just space of k, isn't it? And on average, we only need to try half of them.
Yes.
So space of k over 2, what's next?
And divide by the try rate.
Yep, you can believe that. Can I just return this? No, because space returns int. Alright, let's have space return uint64, shall we? Let's just go full uint64 throughout the program. So we may need to stretch our legs a bit. I'll fix my conversion. Okay, still not happy with that. No result values expected. Right, that's my fault. I'm just being dumb.
Yeah.
What should we return here? Or what type should we return, let's say?
That's try rate divisions might be 64. Do you want to convert that?
Did you say uint64?
Yeah.
Yeah, that seems reasonable. Okay. We're almost ready. I didn't finish off the test, did I? So
Yeah.
let's just add the standard test block. We're going to get a uint64, so we need a uint64 to compare it with. So let's use the old conversion technique. It's nice to be able to write numbers like this with the underscores, isn't it? Anybody seen that syntax before?
I was going to ask about
Yeah.
that. I haven't.
Yeah, it's kind of useful. It's like whenever you get a number that's sort of 4 or 5 or 6 digits, starts to become a bit difficult to see at a glance how big it is. So you can put underscores. As a matter of fact, I think you can put them wherever you like. Doesn't make any difference. But it's more, I think Go just ignores them, but it makes more sense to us to put them where we might put a comma, for example. Or if you're European, maybe a dot. But that should work, shouldn't it? So now what's the problem with this? That it wants a uint64 there as well, doesn't it? So we can do the same thing with that. Is the U justified? I think it is, because none of these things are going to be negative, are they?
Yes.
So fine, let's try it. Oh, mismatch types int and uint64, line 12. Yeah, okay, same thing here, isn't it? Very nice. Okay. Do we believe that? Or is it just passing by coincidence? Because that can happen.
Try
I
with
think
one.
it's believable.
Sorry, say that again.
We should try with one character. Should be getting to 500.
Yeah.
50. Sorry, 50.
Absolutely, yeah. Let's break it on purpose. Put a spanner in. Let's say we want 10,000. We know that's wrong.
Yes.
Okay, good. Yeah. All right.
Okay.
Now I'm a little more confident in that. So, fine. So what could we do next? So we could say what we really want. What we started out by asking for is a function called something like strong enough, isn't it? If Joy sets up a new bank account and she enters a password for it and the website says, sorry, that's not strong enough, how could we implement that function? Any thoughts? We have some of the tools we need, don't we?
It could be a function of like, what the median time is like greater than certain median time. Would that be difficult to crack something of that sort?
Yeah. Yeah, for a given password, we can find the median crack time. So we can say, as the designer of the bank system, we can say we want this password to be not median crackable in less than 100 years.
Yes.
That would be excellent. I'm sure most banks not in fact that strict. And so let's try to test strong enough. We're saying that given, let's use our existing input and our existing try rate, which is extremely low, but it's just going to make things easier for us to work out, isn't it? We're happy about the idea that that number could actually be a lot bigger, aren't we? It could be 1 times 10 to the 9. It's nice to be able to write numbers this way too, isn't it?
Yeah.
Everybody comfortable with what that means?
Yes.
Yeah.
This means 1 times 10
Yes.
to the 9. So let's stick with 1, but let's say perhaps, you know, a modern GPU could do even better than 1 try per second. Let's get our got. Key dot strong enough. What does it have to take?
The password length.
Well, suppose we just pass it the key directly and then it can work out the length for itself, can't it? Should we do that?
Yeah, that could work too.
Let's pass it input then. What else? What's our definition of enough? I kind of gave it away when I said 100 years, didn't I?
Yeah, 100 years converted to seconds. Are we doing, or converting seconds to years? What are we find? Yeah.
Yeah, we need to specify the length of time is the point, isn't it?
Yes.
So let's call it something like min crack time. We understand that means median crack time. And it'll be in a number of seconds just for convenience. Fine. So what's our got? So let's start by asking what type is it going to be?
We're doing the same.
Boolean.
Yep, Boolean sounds right. The name of the function almost tells us that, doesn't it? Strong enough? Yes or no? If the function name is a question to which you can only answer yes or no, it must be Boolean. So that's great. So now we know what our want is, don't we? Or, well, we know it's Boolean, but what's the answer? Is this password strong enough? I'll ask that question to the panel. I'm going to say min crack time equals 100 times 365 times 24 times 60 times 60, right? That's the number of seconds in 100 years? Or
Yes.
I'm not too far off, am I? So I ask again, is this password strong enough? Do we think?
No.
No, nowhere near, is it?
Nowhere near.
We already established that even at a try rate of 1 per second, it only takes 5,000 seconds. A decent Bitcoin machine would crack that in a few nanoseconds. So we're sort of saying we want false, aren't we?
Yes.
And I also need to pass in try rate, clearly, don't I? Even Go is reminding me of this, because it's saying you defined try rate, but you didn't use it. So I need to use it. Okay, and now we can compare want and got. These are not decimals now, they're truth values. And I haven't defined strong enough, but I can do, can't I? And we said it's string, the try rate, and min crack time, all uint64s. It returns bool. Let's just return true. Let's make that a uint64. Pretty sure that will fit. We should be failing, shouldn't we? And we are, which is great. So what can we do here? Joy, any thoughts about this? Perhaps you've already written this code in your attempt to break into various banks. I'll share a link to your excellent blog post on robbing banks with Go. It's well worth a read.
Wow, this is I'm actually learning here, so
I think we all are.
I'm not really sure.
Let's think it through, shall we? So we said the definition of strong enough for our purposes is that the median crack time is greater than some value. 100 years in our case. So we have a function to give us median crack time. Let's call that. What do we need to give it? We need to give it the key and the try rate, which we have. This is looking quite easy, isn't it?
Yes.
So that tells us the median crack time. What can we do with that?
Comparing with the min crack time, if it is greater than min crack time, just return, I guess. Return to the comparator. Yeah.
So we're saying if the median crack time is greater than or equal to, let's say, min crack time, then it is strong enough. So we can return that expression, can't we?
Yes.
Should we try it? What do we think we're going to get?
We should pass this time.
Yeah, we don't think it is strong enough, and we
Yeah.
expect false. So let's see what we get. Good. So now let's make it a little bit longer. Let's see if that's saying that is strong enough. So we're saying if your password is hello, it can't be cracked in less than 100 years, provided that your attackers can try no more than 1 password per second. Which is probably, the answer is probably a lot more, isn't it? So let's make it a bit more realistic. Is that strong enough? No, because it's returning false. So let's try adding more characters until it is strong enough. Yeah, that's saying an 11 character password is strong enough. Is a 10 character password strong enough? Yes. What about that? Right. Okay, so that's interesting, isn't it? So with our pretty vague assumptions, a 9 character password, assuming 100 typable characters, can be cracked within 100 years on average, but if we add 1 more character, it cannot. which is nice. And to be on the safe side, I would crank up this number just a little bit. Let's say, you know, suppose they've got a few machines to throw at it. A few thousand, maybe. That's telling us it's not strong enough. Let's add more characters. Yeah. So even if you increase the try rate by thousands and thousands and thousands, many orders of magnitude, you only need to add a few more characters to put it beyond them, don't you?
Yeah, this is interesting, John. Yeah.
Which makes sense to us, doesn't it? Because every extra character you add multiplies the key space by 100. So it's going to take 100 times as long to search it, which is fantastic. So if you have a password which is secure for a year, just adding an extra character makes it secure for a century. That's awesome. So clearly, you know, the problem with this strong enough function is that we need to put in the try rate, and we don't necessarily know. And one thing that we would like is we wouldn't like to just define a constant for try rate based on what I read online about GPUs, because in 10 years time that try rate is going to be a lot higher, isn't it?
Yep.
So let's think about that for next time. Let's wrap up for today, but let's continue this because I think we're getting somewhere interesting. And we would maybe like to work out, how can we work out what the try rate is? Because one thing we could do is we could say, suppose the attacker has a comparable computer to you. Well, they can probably do as many tries per second as you can. So what if we just did a ton of tries? Let's see how many tries we can do a second. And we'll say, assuming, you know, your attacker's using the same computer you are, then it is or isn't strong enough. How about that?
So maybe they might have even a more powerful computer than we have.
Yeah, exactly. So maybe there's some multiplier that says, like, you know, for enterprise level agency, say it's like 1,000 times whatever your try rate is. For government level agency, you know, 1,000 times more than that, or whatever. But that sounds like a useful line of attack, doesn't it? So let's finish up. So I'll finish by thanking everybody on the panel for your contributions. It's been very nice to have you.
Thank you.
And
Thank
for
you, John.
And I hope to see you all next
It's
time.
great being here.
It was great to have you. Thanks a lot. Bye-bye.
Bye.
Thank you. Bye.